Good morning, everyone. I'm Annabelle from Business University. Today, my team will present our work titled Improving Flood Segmentation Through Boundary-Aware Learning in Radar Imagery. In this work, we investigate whether active boundary loss or ABL can improve flood segmentation performance on SAR imagery using two widely adopted architectures, UNet and DeepLab V3+. Let's begin with the motivation behind this research. Flood mapping plays a critical role in disaster response, damage assessment, and mitigation planning. To perform flood mapping reliably, we use synthetic aperture radar or SAR because unlike optical imagery, it can capture Earth's surface regardless of cloud cover, weather conditions, or daylight. Recent deep learning models such as UNet and DeepLab V3 have achieved impressive segmentation performance. However, these existing approaches often train using region-based loss, such as BCE or binary cross entropy and dice loss. These loss functions encourage overlap between the predicted mass and ground truth, but they do not explicitly optimize the flood boundary. Therefore, it motivates the following research question. Can boundary-aware learning improve flood segmentation beyond conventional region-based optimization? To answer this question, the study has three objectives. First, we evaluate the impact of APL on SAR flood segmentation. Second, we compare two representative segmentation architectures, UNet and DeepLab V3+, under identical training settings. Finally, instead of only evaluating only region overlap, we assess segmentation quality using both region-based metrics and boundary-based metrics. This allows us to determine not only whether segmentation becomes more accurate, but also whether the predicted flood boundaries become more precise. Therefore, we can identify the model that achieves the best overall segmentation performance. Our methodology consists of three stages. First, we pre-process the SEN1 Floods 11 dataset and extract boundary information required for the ABL. Second, we train the two segmentation models, UNet and DeepLab V3, plus using two different loss configurations, the conventional BCE dice loss join loss function and active boundary loss. This results in four model variants for comparison. Finally, we evaluate all models using both region-based and boundary-based metrics to measure overall segmentation quality, as well as boundary accuracy. With that overview, I'll now hand over to Dico, who will explain the active boundary loss formulation and the model architectures in detail.
Thank you, Annabelle. Good morning, everyone. I'm Dico. I will walk you through the core technical components of our methodology, starting with the formulation of active boundary loss, or ABL. As previously mentioned, conventional losses fall short in optimizing edge precision. ABL addresses this limitation by explicitly tracking and optimizing edge precisions by measuring the distance between predicted and ground truth boundary direction. To evaluate our approach under realistic difficult environments, we utilize the SEN1 Floods 11 benchmark dataset. This is a highly curated and manually annotated Sentinel-1 SAR dataset explicitly designed for flood segmentation under challenging backscatter conditions, such as urban areas or dense vegetation. Let's look at the dataset characteristic. It contains 4,831 image chips, each with a standard image size of 512 by 512 pixels. The chips cover 11 historical flood events spanning 14 diverse biomes. It provides dual polarization SAR imagery consisting of both vertical and vertical horizontal channels. The ground truth maps are pixel-level annotation containing this distinct target label, water denoted as 1, non-water denoted as 0, and non-data marked designated as -1 to handle invalid regions. To ensure our findings are robust, we integrated active boundary loss into two very distinct and widely adopted segmentation architectures. The first is UNet, which employs a classic encoder-decoder structure featuring direct skip connection and a ResNet 50 backbone initialized with ImageNet weights. The second one is DeepLab V3+, focused on contextual understanding. It leveraged Arthrospatial Pyramid Pooling or ASPP to extract multi-scale contextual features paired with a ResNet 50 backbone and a dedicated decoder framework designed specifically for sharp boundary recovery. To maintain a completely fair comparison, all four model combinations were trained under identical experimental hyperparameter settings. Using the Adam W optimizer for 50 epochs, a batch size of 4, an initial learning rate of 1 e to the power of minus 5 for the encoder and 1 e minus 4 for the decoder, alongside a cosine annealing learning rate scheduler. The final stage of our methodology involves a comprehensive evaluation strategy, relying solely on standard metrics and hide boundary errors. So we split our evaluation into two distinct categories. First, we utilize a traditional area-based metrics to measure the total regional overlap. This includes MIOU, DICE or F1 score, precision, recall, and overall accuracy. The second one, and most importantly, we introduced three boundary-based metrics to isolate each accuracy. The first one is Hausdorff distance. The second one is average symmetric surface distance or ASSD, and the last one is boundary IOU. With our methodology and experimental setup established, I will now hand over to Prabandari, who will discuss our result and finding.
Okay, thank you, Rico. Now I will present the experimental result. First, let's take a look at the quantitative evaluation. We evaluate the models using two different metrics. The first one is area-based metrics and the second one is boundary-based metrics. For the area-based metrics, UNet with active boundary loss achieved the best overall performance with an MIOU of 0.7283 and the DICE score of 0.8088. Meanwhile, DeepLab V3 Plus with ABL obtained the highest precision, indicating fewer false positive prediction. More importantly, the improvement becomes much clearer when we evaluate the boundary quality. As we can see in the lower table, applying active boundary loss consistently reduces Hausdorff distance and ISSD, while also increasing boundary IOU or BIOU in both architecture. These results indicate that the predicted flood boundaries are closer to the ground truth and have better contour alignment. Overall, the results demonstrate that boundary-aware optimization improved not only segmentation accuracy but also boundary quality. Okay, beside the quantitative evaluation, we also perform a qualitative comparison. On the left, we show the SAR input image together with its corresponding ground truth. And on the right, we compare the segmentation result obtained using the conventional BCE or DICE loss and the proposed active boundary loss. The highlighted region shows that the models trained with ABL produce sharper and more continuous flood boundaries than those trained with the conventional loss. This improvement is especially noticeable around complex water edges, where ABL preserves flood contours more accurately and reduce fragmented prediction. These visual observations are consistent with our quantitative result, confirming that ABL or active boundary loss effectively improve boundary alignment. And finally, I would like to conclude my presentation. This study demonstrates that incorporating ABL or active boundary loss consistently improve both area-based and boundary-based segmentation performance across different network and architectures. Among all evaluated models, unit with ABL achieved the best overall performance, indicating that boundary-aware optimization is particularly effective for preserving fine spatial details in flood segmentation. For future work, we plan to investigate hybrid segmentation architecture, further optimize the ABL hyperparameters, and explore temporal Sentinel-1 SAR imagery to improve flood monitoring across dynamic flood events. That's all I could say. Thank you for your attention. I would be happy to answer any question.